Okay, we will get started here in just a moment. Okay, folks. So let's go ahead and get started. Just a reminder that the second exam is due tonight, so that is due. And so just keep that in mind, as well as the homework that we were discussing before the break, the multiple regression homework. Okay, so that's due tonight as well. So if there are any last minute questions on that, please get that to me. But those are due. Hope you all had a good break. We have a couple more, well, 3 more weeks of this class left. And so there's something, this is the last really kind of new statistical thing that we're going to do in the class. And this thing's called logistic regression. And so the purpose of logistic regression is looking at outcomes that are coded 0 or 1. They're binary. Okay, so whenever you have an outcome, we'll look at an outcome today. Ever been suspended from school? Whenever you have a situation like that, where you are looking at an outcome that truly is dichotomous binary, like ever been suspended from school, or you might be asking of young women, have you ever been pregnant? And that truly is 0 1. You're not kind of pregnant, right? So these outcomes that are binary outcomes, you cannot analyze those type of outcomes really in linear regression, ordinary least squares linear regression. What we have been doing, it is not really statistically feasible to expect to get accurate estimates of the odds of something happening using linear regression when it truly is an outcome that's binary. And also numerically represented in the data set as being coded 0, 1. Okay, so that's what we're looking at here. And for the people doing the graduate course for this course, the graduate paper requires you to look at an outcome using logistic regression. And so what we're going to do today is talk about how this is done. And then I will have a homework, as I said, posted either later on today or tomorrow that you all can, on Thursday will be optional whether or not you'd like to work on that in class. Remember, you don't have to do all the SPS assignments. I think this is going to be number 5. We'll have 2 more. And so up to you whether or not you want to do it. You'll probably, all of you will end up having to do logistic regression, probably to some degree, because I'll have it in the other assignments if you don't do this one. And so you all probably have an opportunity to do it. but it's really no more tedious than running the linear regression SPSS, but it is for these situations where we have binary dependent variables. Okay, so let me share my screen with you. So what we're going to do in SPSS, we're going to take a look at SPSS. We're going to take a look at the variable H1ED7 ever suspended from school. And so we're going to take a look at that, and we're going to take a look at the effect that gender has on this outcome. Okay. So what we want to do is, let me stop sharing this and let me go into SPSS. Okay, let me know if you can't see that. But we have this outcome, ever suspended from school. Okay, and we want to know what the odds of this occurrence is given certain conditions. If say you're male or female, for one. And so what we can do to look at this is, let's first take a look at this variable ever been suspended from school. Okay, and so we want to go to Analyze, Descriptive Statistics, Frequencies. Let me put this back here, delinquency. Let me go to H1ED7. Oops. Display variable names, sort alphabetically. We're looking at H1ED7, and for some reason, let's see, is it further down here? Okay, yeah, H1ED7. So this is just a frequency table. It's always good, remember, to run your variables in the frequency tables before you do anything else. Okay, and so we see that we have 1,801 of the respondents who answered the question who have been suspended from school, and 4,687 have not. Okay, and so that's about the valid percent who responded to it. That's 27.8% versus 72.2%. So clearly, a minority of the sample has been suspended, and so this is what you consider a high-risk group. And so we would like to know, for instance, what impact other factors may have on the occurrence of something like this happening. And to do that, what we want to do is, rather than look at it in terms of linear regression, because the outcome is being measured not on a linear scale, it's just whether something happened or did not happen, we want to use what's called binary logistic regression. Okay, and so to do that, let me go back to we are going to want to take a look at this in binary logistic regression ever been suspended. And we are going to, when I say here, regress suspension on biosex, we are treating a suspension as the dependent variable and biosex or gender as an independent variable. So we want to, we're asking the question then, does one's gender have an impact on whether or not you get suspended from school? Okay, we of course could have looked at this in a chi-square table, just looked at the crosstabs, and we probably would have found that yes, males are more likely to be suspended. But we can look at this in logistic regression, and then after that, we can then add to it additional variables to see what also adds to the odds of being suspended from school, net of other controls. Okay, and so what we want to do is here, here are the answers. So how do we produce this? And we're going to interpret this output in logistic regression. What we want to do is let me share my screen with you and go to here where it says analyze. We want to go down to regression, and we want to go over to where it says binary logistic. Okay, so this is a different type of regression, a different place in the menu screen that you go to do this. Okay, so you go to binary logistic regression. Okay, and let me click out of this. So what we have here, let me just point out here the structure of this is similar to linear regression. We have the dependent variable, and I already have in here the H1ED7. That's the ever been suspended from school variable. Okay. And we also have in here biosex as the independent variable. Now, the independent variables in logistic regression can be measured however they can be measured in linear regression. You have the same 4 categories of measurement, and when you have nominal variables, you want to make dummy categories out of them, but the same rules apply. You have the same type of linear regression going on the independent variable side. It's on the dependent variable side when you have the condition that the dependent variable must be measured in a binary fashion, a 0-1 fashion. Okay, and so we can also, let me just show you. If we look back at, oops, that didn't work. Oops. Trying to get to, let me. Oh, my screen is being funny for some reason. Okay, let's see if I can try to, I'm just trying to get to the variable view screen. Okay, let me, no, this should work for you guys now. Let me get back to it. Okay, oh, sorry, just a moment. Yeah, so notice in that SPSS output, it didn't clearly show that this thing was coded 0-1, but it in fact is, this variable is a coded 0-1 variable. So we can then look at the odds of how gender may affect whether or not someone is suspended from school. Okay, so that is the major difference from the linear regression, the stuff that we were just doing, that the dependent variable has to be coded 0-1 for this, for the binary logistic regression. Okay. So we want to go to regression. We want to go to linear. I'm sorry, not linear. We want to go to binary logistic. Okay. All right. And for this one, I'm just doing H1ED7. That's the suspension as a dependent variable, and biosex as an independent variable. Now, there's lots of other options here, like there usually is within the regression options, regression procedures, but we just need to leave it the simple way, just with this where it says block 1 of 1. We don't need to mess with anything else. That's just where you put the independent variables in. Okay, and so when we run the regression equation, What I want to focus on here initially is this table at the very bottom. This table at the bottom is very similar to the output that one gets when you run the linear regression, okay? So here we have a constant, which is A in the regression equation, and we also have unstandardized beta coefficients. Now, these are actually called logits because they're from the linear or from the binary logistic regression. They're on the effect on the log odds of something happening. So what you're seeing here, this is the effect of gender on the odds of being suspended from school. Now, the effect here is negative. So the way that we interpret that is the same way we've interpreted the effect of biosex in the linear regression. It's for every unit increase in this variable, biosex, that's the impact on the odds, on the log odds of being suspended. If you recall that biosex in this SPSS data is measured 1 for male and 2 for female. So when you say for every unit increase in biosex, you're going from male to female. And so what this is saying is that females coded as 2 compared to males coded as 1, females have a lower log odds of being suspended from school compared to males. So it's because it's going to be comparing it to the level of measurement below 2. So because it just compares what the effect of a unit increase is. And so because this is just a 2-level measurement, it's 1 for male, 2 for female. So what we get then, we know the way you interpret that is it would be it's looking at the difference in the odds of suspension for males versus females, and it's showing that females have a lower log odds of being suspended. Okay, and so here is that's how you interpret that. Okay, this is the standard error for the logit, similar to how we have a standard error in the estimate for unstandardized betas and linear regression. The significance of the betas and the unstandardized betas in logistic regression are calculated by what's called a Wald chi-square statistic. So it's actually it's on a chi-square distribution to determine whether or not the effect of gender is itself statistically significant. And so there is a significance test associated with the logits or the log odd effects in binary logistic regression. And so the significance test is shown here as the p-value being 0.000. And so you can conclude that, yeah, that gender makes a difference in terms of the probability or the log odds of being suspended. So the way, though, that we can interpret this a little bit more intuitively is we want to look at the exponentiated version of this variable. So if we express b as an exponent of the constant e, the mathematical constant e, b expresses a power of e, so b is an exponent of e, of the constant e, then what we get is, I forget what e is, 1.2 something. It's a constant, and so it's expressed as a constant of that because it's in the log odds, and that makes it interpretable as the effect on the odds of gender. Okay, so this is the exponentiated version of this beta. So if we would say what is the effect of b when expressed as a power of the constant e, this is what we get. So that it's doing that automatically for you. And so this is expressed, this number right here is the odds, the effect on the odds of being suspended, okay? And so the effect on the odds, or what's called the odds ratio. Okay, so this is what's called the odds ratio, or the effect on the odds, because this is on the log odds, which is not really math, it's not intuitively interpretable. And so what happens is most times we want to interpret this in terms of the exponentiated beta. And so this is the exponentiated beta, the effect on the odds of it occurring. And so because this is below 1, you know that it's lowering the odds. If it's above 1, then it would be raising the odds. Because if the probability of something happening is 0.5 and the probability of it not happening is also 0.5, then the odds of it happening, of something, if that's the case, then that would be 1. And so there is no greater or lesser odds of the thing occurring. And so because this is less than 1, that means it's lowering the odds of the thing occurring, and that thing being suspended from school. Okay, and so you will never have an exponentiated beta term that is negative. Whenever you express B, these logits, in terms of an exponent of E, the constant E, it will, if it's negative, it will always return a value that's less than 1. Okay, and so that's what that is. That is exponentiated beta. This exponentiated negative 0.957 will give you the value 0.384. And because that's below the value 1, we know that it's lowering the odds of the dependent variable occurring, okay? And the way to further interpret that, so it's more, I guess, intuitive, is if you take that number and subtract it from 1, that is the percent that it lowers the odds of something occurring, that being suspended. And so let me show you on the Moodle page what I'm talking about. Okay. And so here is our unstandardized beta, which is the effect of gender on the log odds of being suspended, and it's negative. And we interpret that as that's showing that 1 unit increase in gender, and that thing is measured, 1 is male, 2 is female. So females have a lower odds of it happening. So that's the effect on the log odds. If we express this as a power exponent of the constant E, that will return the odds ratio, the effect on the odds. Okay, so this is more interpretable. So we know that because 0.384 is less than 1, we know that being female is lowering your odds of being suspended from school. Okay, and so the way that you further can interpret this is being female as compared to male lowers the odds of school suspension by, and what you want to do is you can plug it into this formula where it's taking into account, so here's your unstandardized beta, and here is it's being expressed as a power of E. And so to get it expressed as an exponent, this works on calculators. It also works in Google or and Excel, is that you have to put this little symbol here after the constant E. And then that is subtracted by 1 and multiplied by 100. And so what that is doing is giving you this value of 61.59. Okay, and so that, if you take 1 minus 0.384, that will give you 0.6159. Expressed as a percent, what it's showing is that being female lowers your odds of being suspended from school compared to males by 61.59%. So being female lowers the odds of being suspended from school by 61.59%. And again, the way that we got there is we're just looking at in linear, or I'm sorry, not linear, binary logistic regression. We're looking at ever being suspended from school as a dependent variable, biosec is the independent variable. This is the impact of gender or biosex. And if we exponentiate that, the negatives will go away. And if it's less than 1, the odds ratio is less than 1, we know it's lowering the odds. Well, how much is it lowering the odds by based on this figure here, 0.384? It's 1 minus that times 100. You convert that into a percent, and it's lowering the odds by 61.59%. Okay. And so that is how you would interpret in a binary logistic regression the effect of one independent variable on the dependent variable. Okay. If we want to take a look at regression of being suspended on 2 variables, delinquency and biosex, we can quite easily do that. We can do that just like we have done it before with linear regression. We have a multiple linear regression. In this case, though, we have a regression that's logistic. And so we are going to look at this model where we have suspension as the dependent variable, and then we will have delinquency and biosex as the independent variables. Okay. And so we will also be able to do what's called predicted probability, given certain settings on your variables, given that you're female and non-delinquent or male and highly delinquent. What is the predicted probability of being suspended from school? Okay. So we'll do all those things. Okay. So let's first run the binary logistic regression. Okay. So we want to have suspended from school, delinquency, and then gender in there. Okay. So in order to do that, we'll go up to analyze, and we again go to regression. We go to binary logistic regression. And we want to go into, let's put this over here. Now, what I did, let me make that delinquency scale just so people are aware of what we're doing here. We're making the delinquency scale as an independent variable. I already have it made, but I'll just show people one more time what we're doing to make the delinquency scale. To make that scale, it's the sum of the items H1 DS 1 through 15. Okay, and so to get the exact output, I just recalled on this, I didn't recode to get rid of the missing. I just made it like this. Okay, so I didn't recode to get rid of the missing, and so it is just simply the sum. Go to compute variable. Delinquency equals the sum of H1 DS 1 through 15. Okay, that's all that was, so people are clear where that is coming from. Okay, so I already did that, made that independent variable. So we're looking at the effect of gender and delinquency on suspension from school. Okay, so let's go back to regression and go to binary logistic. And let's put in, put in my delinquency, and let's put in a biosex. That's the order in which I say. It doesn't matter what order you put it in. I just did that just to be consistent with the equation I already have written on Moodle. Okay, so we're looking at that as our model of this binary outcome. Okay. So here is what we get for the output. Okay, so let me first go back to the beginning here and all of this output that it gives you. So it starts actually up here where it says block 0 beginning block. It's just looking at the number of cases for which you observe a suspension and non-suspension. And so you see that frequency table there. What you have here is a intercept only model. It is just, it's looking at just the intercept by itself in the model, which is not too terribly useful. And then it adds in the additional variables. There is an overall omnibus test to see if any of the variables below are statistically significant. This is a chi-square test, kind of like the F-test in linear regression. But that stuff is not too terribly important. This stuff up here is not. What is important, though, is taking a look at the model summary right here. Now, there are a couple R-square statistics. There's the Cox-Snell R-square, and then there's the Nagelkerke R-square. Now, I believe the Nagelkerke R-square will typically show you a higher R-square value than the Cox-Snell. That is a lower bound. But both of these statistics are interpreted the same way as the R-square statistics in linear regression. That is, how much of the variation in some outcome is being explained by the independent variables. And so if we take the Nagelkerke R-square, which I think assumes that the dependent variable is a measure of an underlying risk factor for which you just have a binary indicator, so it'll always be a little bit higher, that would it be interpreted as biological sex, or biosex, the gender indicator, and delinquency explain about 16.3% of the variation in whether or not respondents were suspended from school. Okay, so it explains about 16.3% because it's out of proportion of can't get higher than 1, and so it's out of so it's 16.3% of the variation in whether or not someone was suspended from school can be explained according to the model, which includes delinquency and biosex, can be explained by those two variables, two variables combined. Okay, and so that's of importance. The classification table, that's not too terribly important for our purposes right here, but let's go back down again to this output here. And so we have output. Now we have a multiple regression analysis here, but it's in binary logistic regression. And so we can see that we have delinquency in the model now. We also have biosex. So biosex, we'll start with this. This is interpreted the same way. So for every unit increase in biological sex, that's going from male to female. This is the effect on the log odds of suspension. And so this is lowering the log odds of suspension. So if you exponentiate that, it's lowering the log odds here. If you go 1 minus that would be the percent that it's lowering the log odds by. If you go 1 minus 0.43, that's the percent that it's dropping the odds. That's the percent difference between males and females. So we know that it's lowering the odds. We know that gender has effect of lowering the odds, that is, females have lower odds. If we just simply looking at this knowing it's lower than 1, right? So if it's below 1, it's lowering the odds. Okay, so by what percent is it lowering the odds? Well, it's just 1 minus 0.432. So yeah, okay, so we have also this effect of delinquency in the model. Okay, now delinquency is a variable that has a range of values from 0 to 15, and so the effect of delinquency here is interpreted like you would any other variable in linear regression. For every unit increase in delinquency, so every point higher in delinquency, this is the effect on the log odds of suspension. And so the effect is positive, the beta is positive. And so we know that the more delinquent the kid is, the higher the odds of him or her being suspended from school, which makes total sense. Okay, and so if we look across here, we see the significance tests associated with these variables, and we see that both are statistically significant. Okay, and so if we see the exponentiated beta for this, since this is a positive beta, if you express that b as a power of the constant e, then what you'll get is this number, 1.134. Okay, and so what that is saying is that for every unit increase in delinquency, the odds of being suspended goes up by about 13.4%. So it's the difference of this number from 1 is the percent change that occurs in the odds of suspension for every unit increase in delinquency. And so since this exponentiated beta, see, this is above 1. And so it's saying for every unit increase in delinquency, the odds of being suspended goes up by 13.4%. And if you plug that this value, 1.26, back into that equation that I showed you originally, that had ever suspended as a dependent variable and just gender in there as the independent variable, that's what you would find. You would find the answer of 13.4, which is interpreted as 13.4% increase in the odds of being suspended for every unit increase in delinquency. So yeah, the interpretation is just really very, very similar to what we did in linear regression, except for the fact you're interpreting it in terms of the impact on the odds, and that you can do that after you have exponentiated these betas. But SPSS does it for you already over here in this column. Okay, and so you don't have to do that. So the constant, we should maybe mention that here. The constant is involved in your formula for predicted probability, which we'll do here in a moment. But it's saying that when delinquency and biological sex are taken into account, the overall odds of being suspended are less than 1. So it's less than an even chance of being suspended from school, because most, as we saw from the frequency table, that makes sense because most of them were not suspended from school. So you got from the get-go, you have a less than even odds of being suspended from school, and then it's adjusted accordingly based on your in this model, based on your delinquency, self-reported delinquency, and based on your gender. Okay, and so we can do predicted probability. Predicted probability ranges from 0 to 1, and this is an outcome that's measured 0, 1, and so we can do a predicted probability of this happening based on a statistical profile. Let's take into account, in this case, their gender and their self-reported delinquency, and that's what is being done here in the SPS. In the Moodle. What we're looking at here is the components from the SPSS output put into this equation. And so the equation here is the same equation that we used for linear regression, except for all of it is raised as an exponent of a constant, the constant e, and then it's divided by 1 plus that value, and that will give you the predicted probability. So this is plugging in values based on the unstandardized beta. So a negative 0.28, that is the constant, the unstandardized constant, and then we got a 0.126 for delinquency, and then we've got a 0.84 for the effect of gender. And so those values right here are coming from here. So this is being plugged in here for the value for A, and then for our betas, we have the effect of delinquency, and we have the effect of biological sex. Okay, and all of those are being multiplied by X values that you want to set. And so, again, these are provided to you, what you plug into the equation, and then you have to say, okay, well, what we want a predicted probability of suspension for a male who is highly delinquent. Okay, and so if we want that as the statistical profile of the person, we want to know the odds of the predicted probability that he will be suspended from school. Then what we want to do is, as I'm showing you here on Moodle here, is we're, so this is our, the effect of this 0.126. So here's the constant first. We start off with that, and then we add to it the effect of delinquency. And then we say, we want to say, okay, well, we're on a highly delinquent kid. And so I think 15 is the highest score we can get on the delinquency scale. So I multiplied that by 15 because it's just B times X, just like what it was in linear regression. For a male, okay, so the effect of gender here in the model was negative 0.84. And so we want to make this person male. And so males are coded as 1. So we put a 1 there. And so we can tell by making the person male, it is necessarily going to, because this effect is negative, it's going to lower the odds of suspension compared to being female. Okay, and then that is all divided by 1 plus this whole thing over again. That is the equation for the predicted probability of some occurrence. And so it's very similar to linear regression, except for the fact that you're adding in the fact that you are raising the whole equation as being an exponent, a power of the constant E. And then it's over 1 plus that whole equation. And so when we do that, and you could just plug that into Google, when we do that, we get the answer of 0.99. And so that this can't get any higher than 1. So that's pretty much saying that, yeah, that a male who is that delinquent, given the effect of delinquency and gender on the odds of suspension, that he's got pretty much a 99% or probability of 0.99 that person at some point in their youth will be suspended from school. Okay, and so that's a very, very high probability. Now down here, I'm doing it for non-delinquent female. Okay, and so we have all the same predictors, right? We have all the same we have the same constant and everything, and the same unstandardized betas. But here we are I'm plugging in the values for delinquency. So I want this being a non-delinquent person. And so 0 does exist on the delinquency scale. Somebody can have a 0 delinquency, so they're non-delinquent, and they are female. Okay, and so this is going to lower the odds even more so because someone is female. So it's going to multiply by 2. Okay, and so you repeat all that, and so the odds of a non-delinquent female being suspended from school is only 0.126 out of a high max score of 1. And so that's considerably a lower probability of a person with this statistical profile, female non-delinquent, of being suspended from school, which makes complete sense. Okay, and so again, we are just plugging in numbers for the X values that are for delinquency and for gender here. And so that's where we're coming up with these values, the negative 0.288, 126, and negative 0.840, all were taken from the SPS output. This is this is just, if in a calculator or in Google, you plug those values in. Those are the answers that you are going to get. Okay. So we can, okay, are there questions about any of that if somebody want me to go back to anything from the SPS output at this point, highlight something or re-explain something where these numbers are coming from? Okay, so that is for an outcome that is coded binary, and it really only makes sense to code it binary. There are other variables that are also truly binary, like the ever been pregnant one. That's truly binary. You could never do that as a dependent variable linear regression. Logistic regression, it's no problem. You can look at these outcomes that are yes, either it happened or it didn't happen. Okay. Well, we can also, though, for some variables, we might want to just know just if there is an effect on the odds of any occurrence of something. And so we might want to know, well, we know that not all kids are delinquent. It looks like most are to some small degree, but really what we're concerned with is if there is any delinquency at all in their self-reported record. And so you can use logistic regression when you have a continuous variable like delinquency or something else that could be any response, any positive response to any of these items, let's say any of the substance use items, any items like any positive response to violence, anything like that, where you want to say, okay, did they say yes to any of these things? These are all sort of very high risk behaviors, things that occur very infrequently. So we want to kind of cast a wide net here and say, did you do any of these things? I'm going to give you a 1. And if you didn't do any of them, I'll give you a 0. Well, once you do that and you recode a variable so it is a binary or dichotomous like that, coded 0, 1, then you can put it in binary logistic regression and look at it in that. Okay, so let's do this. I'm going to recode my delinquency variable so it's 0, 1, and then I'm going to include gender and the picture vocabulary test. AHPVT. Okay, so this will be the last one we do today, and then we'll just go. I want to go over the results and make sure people from a second example get how to interpret this. Okay, so first of all, what I want to do is I want to recode my delinquency. So I have a dummy variable delinquency indicator. Okay, and so what I want to come in and do, I want to go to transform, recode into different variable. Let me reset this stuff. Let me go to my delinquency variable, and I'll just call it, dummy delinquency. You have to hit change, old new values. Okay, and I'll say if you were a 0, you get to stay as 0. If you were a any other values, all other values, then you become a 1. Okay, and then if you're a system or user missing, you get to stay missing. We'll just keep the missing. Not that it matters that much, there weren't too many missings, but there were some. So yeah, what we did there was saying if, okay, you're a 0, you're gonna stay as 0. Everybody else gets to become a 1, and then the missings become missing. Okay, and so that's going to be our dummy delinquency. And let me, oops, okay. All right, so let me just run the frequencies on that. After we make a variable, always a good idea. Oops, let me sort by file order to make sure that we've got a variable to analyze. Okay, so yeah, here's our variable dummy delinquency. We've got, yeah, most of them have been involved in some delinquent act, 77.4%, where we have the teetotalers here who have apparently not done anything bad at all, 22.6%. Okay, so you have that as your binary outcome. Let's go ahead and take a look at that in binary logistic regression. We want to go down to regression binary logistic. Okay, and we're going to put in for the dependent variable, the delinquency dummy. And Biosex is already in there. Let's put in the AHPVT. Remember, that's the picture of vocabulary test. It's an indicator of verbal IQ, and these things tend to be negatively correlated with high-risk behaviors such as delinquency and violence and other things. So we'll take a look at the effect of this on the odds of ever being delinquent. Okay, and so here is our output. Okay, and so we're seeing that only 0.7% of the variation in the outcome of delinquencies being explained by these two variables. So not much being explained here in terms of the overall variation, whether or not someone is delinquent. But we do have some significant coefficients down below. At least we have one. Okay, so let's look at this, the effect of biological sex on the odds of being delinquent. That's negative 0.306. That's on the log odds. So if we exponentiate that, we're going to get a 0.736, and so 1 minus 0.736 is, let me, okay, oops. 1 minus 0.736, we get a 0.264, and so that means that the odds are lowered by 26.4%. 24 point, what did I say it was? 0.264. So it's lowering the odds by 26.4%. Sorry. Okay. So that is the effect of biological sex. It's lowering the odds by 26.4%. And that is 1 minus, we get there by going 1 minus a 0.736. That's how much it's lowering the odds by, 1 minus that. And so that would be interpreted as that's how much lower percent odds of being delinquent females are compared to males. Okay, same thing as before. This is the effect of the picture vocabulary test. Now it is actually positive, interestingly. Expect it probably be negative, but it is positive. So the higher the score, it's increasing the odds. This is the effect on the log odds. As we exponentiate that, the effect here, the significance is 0.089. And so that is a non-significant effect. And so we don't really want to put too much weight or credibility on this very small impact that this thing has on the odds, raising for every point increase on the picture vocabulary test, the odds of being delinquent goes up by 0.3%. But it turns out that that's not even a significant effect. Okay, and so we should not really be too concerned, at least based on this binary measure of delinquency, the effect that this has, the effect that the AdHealth picture vocabulary test has on it. So you're not finding a significant effect. So that is another example there for you. In your book, the SPSS book, this book, chapter 25, there are examples of logistic regression that you can take a look at. But I think that is all I want to do for today. If there are questions about anything, people can stick around. I will have a homework post on this. We'll go over that on Thursday. I'll post that before Thursday. We'll do some logistic regression exercises. But this is all we have for today. So I think that does it. Are there questions from anyone about anything that we did today? If not, you guys are all free to go. We will pick up with this on Thursday, then back in the lab. I will post the homework for it prior to that, and the exams. Remember, those are due tonight. So please make sure and get those in. Okay. You are all good to go. Unless there's something you want to discuss with me, you can stick around. Okay.
Professor Saffron, next Tuesday, I'm not going to be able to make class.
Okay.
I was invited back for the first written psychological exam for the
Okay.
hiring of the Department of Corrections. So I just wanted to give you a week heads up on that one because it starts at 8 a.m. and it's going to be 8 hours. So I'm not even going to be out of the psych exam by the time class starts.